Hey, Chem people. I'm just gonna go over you getting to watch me do sample A, that type of problem, practice A type of problem, and just chat about it briefly. So I'm gonna do one that's not in the book, that I think it'll be an obvious one. Show you how this problem works, and then maybe I'll do the sample problem, and then you're responsible for the 3 practice and 1 from the section review. This is all for Thursday stuff. So, okay, the type of problem that we got here is where we get to actually figure out, using the thermodynamic data given, we're going to be figuring out the the melting, boiling points, freezing, whatever you want to call them, right? The phase change points of different materials. You need this particular handout right here, 53A, was in your stuff. And if you don't have this, you can go to the back of the book in the appendix and you'll find the same exact information. These are the molar enthalpies and entropies. Remember, enthalpies are delta H and entropies are delta S of both fusion, that's when something melts or freezes, and vaporization, when something either evaporates, boils, or condenses, depending on which way you're going. If we're going fusion and vaporization, we're assuming we're going solid to liquid or liquid to gas. So we're in this section which is about how we're measuring the enthalpies and entropies when we go through phase changes. Okay? And we're saying that Gibbs energy actually applies in a way to these two. You got some heating curves and stuff like you did with the water. You find that it goes up at a general rate until it goes through a phase change and then it kind of flattens out. Some of you experienced that by doing the experiment for about 5 times as long as you were supposed to, and then you had to do it again. So what we do here is we say that we've got a tipping place. When we're going through a phase change, if we lower the amount of energy, we're going to drop back down. Let's say we're trying to evaporate something. We're trying to boil something. We get up to its boiling point, and if we drop the energy down, that thing's going to go back to the liquid state. And if we raise the temperature, we keep adding heat, we're eventually going to bump that thing up into the gas phase. Same thing if it's melting and freezing. If we drop the temperature, if we take some heat out, then it's going to freeze, and if we send that up, it's all going to melt. What we find is that when delta G, when the Gibbs energy is equal to 0, we're right at equilibrium. We're right at the sweet spot where we've got 2 phases at the same time. We've got either solid and liquid or liquid and gas. It's balancing, teetering right there where it could go either way, depending on if we add energy or if we take away energy. So if delta G is 0 in this equation, this is almost like, how we do stuff in math. We say, the polynomial equals 0. Well, now we can rearrange the parts here of this to solve for stuff. So I'm going to leave the delta H on this side, and we're going to add T delta S to this side. And then the cool thing that I can do with that is then if I can get T on one side by itself, and that will be either the temperature where something freezes or melts, or it'll be the temperature at which something boils or condenses. Okay, now on this sheet there it says fusion. Fusion is when something melts. So we're going to have one set of data that is, well, it's the T melting point, delta H for fusion, and delta S for fusion of these various substances. We're going to focus on water for the first, because we know at what temperatures we ought to expect those things to happen. 273 Kelvin and 373 Kelvin, or 0 Celsius and 100 Celsius, if you want to think of it in that. This only works if we do it in Kelvin, though, because we can't have negatives in this problem. So divide both sides by delta S, and we'll get the T, and then let's do specifically the melting point is going to be equal to delta H of fusion divided by the delta S for fusion. Again, these values have already been determined And we're going to use one that's very familiar to us just to prove the point. Okay? And we will do the exact same thing if we're trying to find the vaporization point or the boiling point. We're going to use delta H of vaporization compared to delta S of vaporization. We'll use both these two sets of equations. I've got over here the data off of this sheet for water. Here's water's change in H for fusion and change in S for fusion. If you note, the fusion, the delta H values are in kilojoules, but the delta S units are in joules. So what we want to do is we want to make them into the same type of units, and then when we do multiplication, we're multiplying apples with apples. So this turns into 6,010 joules per mole, and then we've got here 22.0 joules per mole Kelvin. When you divide one by the other, all the units cancel except for Kelvin, and that's what you get. You get a melting point or a boiling point in kelvins. Now, this top data here is for fusion. Okay? It's for fusion. That is, it's for melting. So, for water, delta S is 6,010 joules per mole, and its delta S value is 22.0 joules per mole Kelvin. Quick calculation with that. 6010 divided by 22 yields an answer of 273.18 Kelvin, which is pretty spot on. We're only allowed 3 significant figures here, though, so we get our estimated answer 273, which is the data value that we're looking for water. Okay, that's pretty cool. We do the same thing with vaporization for water. Delta H for water is 40.7 kilojoules per mole, which translates to 40,700. And the entropy, change in entropy of vaporization is 108.8. And so we're going to do the same thing. We're just going to use those numbers. I'm going to leave the units off because I know that the units are going to end up being kelvins. This one comes awfully close. It's not exact numbers because we've got estimates here, but it gets 374, which is close enough, right? It's close enough. You could do that for any of the things on this list: nitrogen, hydrogen sulfide, bromide, benzene, or lead. Or in a problem like the sample problem in the book, they're going to give you a lot of those values. And you would still just use the exact same types of setups to get us our melting point and boiling point. Again, this is the place where they're at equilibrium, where we're right between phases. Both of these are right in between phases, and we're finding the sweet spot. If we raise the temperature, it'll bump it up into the gas phase. Or sorry, this one, if you bump it up, it'll go up into the liquid phase. If you bump it down, you drop the temperature, you'll go back into the freezing, go freeze and get solid. The book does, what is it? What is the compound? Mercury. Oh. Okay. And you see mercury is not on here, so you're going to have to use the data that they give you in the book, but all this is exactly the same because we're finding the equilibrium point, which for our case happens to be melting or boiling points. So we're just listing off here the information for this is for mercury. Delta H of fusion is 11.42. We got delta S of fusion 9.79. Both of those are joules, I believe. Joules, 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 joules. Yeah, there's no changing of units necessary here. So that makes the math pretty nice and straightforward. We also have delta H of vaporization, 294.7, and delta S of vaporization is 93.8. Righto. Any other information we need here? Nope. Molar mass. Minor calculation. Joules per gram. Oh, they're giving us grams of this stuff. Yeah. Enthalpy fusion of mercury, the molar enthalpy fusion, the enthalpy molar, calculate the melting point and boiling point. Given 200.59 grams per mole, and we are working with a certain amount of stuff. Why do we even care about that? Oh, should have just given us the numbers. Okay, so we're looking at delta H being 2291 joules per mole. Okay, 2291. What, somebody's trying to talk to me or something? We've got delta H vaporization, 59,111. 11, all right, 59,111, 110. And then they got the S values in there as well. We just had to twiddle with the first ones in the book for whatever reason. Okay, so those look like they stay the same. Okay, so we got the first one here of 2291 over 9.79. And the second one here being 59,110 over 93.8. 2291 over 9.79. And yeah, okay. Easy calculations for the calculator. 234 Kelvin and 630 Kelvin. Now we already know this is mercury. And so mercury is already melted by the time we are at room temperature, and it boils at 630. Okay, so we just needed the information there. I think the rest of them will pretty much give you all the values that you need, and you're just going to plug them in to the equation. Let's see. They don't have one step's all given there. Sulfur dioxide is not on this list either, and ammonia is not on that list. So all the information is actually in the problem, but this is what you need in order to do that. Make sure that, like the first problem I did with water, make sure that everything's in joules, so that when you're adding stuff together, it all adds the right way. All right, if you got questions, we can do a chat thing, but I just wanted to demonstrate. I think I did a better job on the water than I did on the sample problem, but it does work, and it's kind of a cool concept. So hope that helps. Get that stuff done and get it to me for Friday. Thanks.